Okay, so we had a discussion of numeric approximation of integrals in the last section, and we did some examples on it, and I hope that gets you guys started with the homework or help you get through the homework. Next topic of discussion, of course, is the last part of this techniques section of the book, which is the solving what we call improper integrals. Now, if you remember at the beginning of the quarter, when I started talking about the integrations, I started by saying, well, suppose my f of x is a continuous function over a closed interval, a positive continuous function over a closed interval. And almost immediately in the next section, we dropped the requirement for it to be positive. We say it could be negative, and that would be okay. We could still interpret what that means. But we never dropped the requirement that it is continuous, nor did we drop the requirement that it's over a closed interval. So a closed bounded interval. So those two requirements never went away. And it's time now to remove those two requirements as well, at least to some extent. Which brings us to the concept of improper integral. So we have two types of, Stuart likes to call them two types of improper integrals. One is the one where you have either one or both of your bounds are infinites. So that will be type 1, where one of your bounds, or both your bounds, any of these forms would be an improper integral of type 1. So you're removing the boundedness of the interval. You know how in here it goes from A to B and that was it. There was no infinite nature of that. That was just it goes from A to B. But now in this new topic, or in today's lecture, we're going to deal with situations where it is not from a finite number to another finite number. It's probably from a finite number to infinite number, or an infinite to finite, or from infinite to negative infinite to positive infinite. So that's our new challenge to be able to have that. And of course, type 2 involves discontinuity. Type 2 is if I have integral from A to B, either not continuous at A or at B or both or somewhere in between. Now, somewhere in between, if it's somewhere in between, then we're going to break it into two intervals, and then we're going to treat it like one of the other two cases. So that's not really a special case, but still, we're gonna talk about it. We're gonna cover it. So what happens in the situation where we have interval from A to infinity, or negative infinity to A, or say negative to positive infinity? Well, let's first deal with the cases, the simple case, or the more basic case, where it's integral from negative a number to infinity. So, for example, if I have integral from, say, 1 to infinity of e to the negative x dx, and I'm trying to calculate this. Now, this function, e to the negative x, is in fact a continuous function. And I'm integrating from 1 to infinity. So I'm trying to calculate the area below the curve here. Now, you can't do the antiderivative and plug in the bounds, because you cannot plug in the infinite bounds. It's not a number, so you cannot plug it in. So what we do is we're going to say, okay, why don't we do this? Why don't we calculate if this is my function e to the negative x, and this is 1, of course. And I calculate the value, the integral, the area from, say, 1 to some b, and then I let my b go to infinity. So I'm going to calculate this, I'm going to take the limit as b goes to infinity of integral from 1 to b. Now this is a definite integral. I can calculate that. So I'm going to say, well, that's going to be limit as b goes to infinity of 1 over negative 1, because that's e to the negative x as x goes from 1 to b. Of course, that's going to be a limit. Don't drop your limit, and make sure that your limit it covers everything that should be under the limit. Well, I'll explain what I mean in next examples. Negative e to the negative b minus negative e to the negative 1. Now, as b goes to infinity, e to the negative b is like going to negative infinity, e to the power of negative infinity. So this part actually goes to 0. Negative negative is positive. E to the negative 1 is 1 over e, so the answer is 1. So that's how you calculate integral when you have one of your bounds, say the upper bound is positive infinity. So in a way, you just calculate the definite integral, and then you let the upper bound go towards infinity. Let's do one more example here. Suppose I have integral from 0 to infinity of 1 over x squared plus 1. Okay, so I'm going to rewrite this as limit as b goes to infinity of integral from 0 to b of 1 over x squared plus 1. It's worth noting that once you write it like this, once this is written, you treat this like a definite integral. So you can apply any of the techniques of integration we talked about, substitution, integration by parts, trig sub, any of those. You can apply it here because now that's a definite integral and you treat it like such. What you have to deal with later is you have to deal with the limit of that. But to calculate that, you can apply all the techniques you learn. There's going to be limit as b goes to infinity of, remember the antiderivative of 1 over x squared plus 1 is tan inverse of x from 0 to b, which is limit as b goes to infinity of tan inverse of b minus tan inverse of 0. Now remember, arctangent or tan inverse looks something like this. And it has asymptotes of negative pi over 2 and pi over 2. That's something from trig. You can graph it if you want on a calculator and you'll see the same thing. So as b goes to infinity, your arctangent goes to pi over 2. And arctangent of 0, of course, is 0, so the answer is going to be pi over 2. Okay. So that's how you handle when you have upper bound is a negative, that is positive infinity. That's how you handle that. Then the next case is where we have lower bound being in infinity or negative infinity. You can switch it. So what if you have situation like negative infinity to say 0? Let's just deal with the same function, 1 over x squared plus 1. Well, you do the same thing. You're going to still do the same thing. You're going to let one of the infinite bounds to be b, and you take a limit as b goes to negative infinity. Another way of handling is you can call it negative b and let b goes to infinity because there's a negative there, so that negative will just carry through. Once again, you treat this just like a definite integral. So it's going to be limit as b goes to negative infinity of tan inverse of x from b to 0, which is limit as b goes to negative infinity of tan inverse of 0 minus tan inverse of b. Tan inverse of 0 is 0. As b goes to negative infinity, tan inverse, as b goes to negative infinity, tan inverse goes to negative pi over 2. It's not surprising because 1 over x squared plus 1 is a symmetric shape. It's an even function with respect to y-axis. So whatever the area is above 0 and the area is below 0 would have to be the same. So it's not a surprising result, but it's nice to see how the process will go. Okay. So let's do another problem. Let's do negative infinity to 0 of z e to the 2z dz. Because this is problem number 19 of your book in 7.8. Integral from negative infinity to 0 of z e to the 2z dz. I'm not a big fan of having z and 2 in the same problem, but yet there is. So what I'm going to do is I'm going to first change it to the limit form, limit as b goes to infinity or negative infinity. Let's do negative infinity. I think that's a little bit smoother for our writing. Integral b to 0 of z e to the 2z dz. I put the line for my z so you can distinguish between that and 2. Then I'm going to do integration by part. I'm going to let u be e to be z, du to be e to the 2z dz, dv, sorry. The v would be 1 over 2 e to the 2z, du is dz. As I said, basically you just treat this as a definite integral, whatever that is, you just apply the process to. But remember, the limit should go for the whole thing. So I get limit as b goes to negative infinity of uv z over 2 e to the 2z from b to 0 minus v du minus 1/2 integral 0 to b of e to the 2z dz. That's the v du part. Remember, the limit is for both of them. So it's going to be limit as b goes to a negative infinity of z0 minus b. And of course, antiderivative, this is 1/2 e to the 2z again. So it's going to be minus 1/4 e to the 2b, or plug in 2, or b in for z, plus 1/4 e to the 0. So this is 0 regardless of the limit. As b goes to negative infinity, I have a situation here. So actually, let's write it out, and we're going to discuss it in a second. B goes to negative infinity of negative b over 2 e to the 2b. As b goes to negative infinity, 2b goes to negative infinity. E to a negative infinite power goes to 0. So that part is gone. And the last part is just going to give you 1/4. But the question is what happens here. Now, let me explain what the dilemma is. As b goes to negative infinity, this part goes to infinity. E to the 2b goes to 0. So we have what we call in Math 1a as an indeterminate form. We have something that goes to infinity, something that goes to 0. The product of them could have different values depending on, as I said, in a way, it's the speed of how fast they go to 0. But we don't want to use that language because speeds can be misinterpreted and applied incorrectly. So I'll do this limit on the side. So I have limit as b goes to negative infinity of negative b over 2 e to the negative 2b. So I'm going to bring the e to the negative 2b down. Now what I have is something that goes to infinity. Also, because negative b goes to negative infinity, negative 2b goes to positive infinity. So this also goes to infinity. So I have what we call in Math 1a as an infinite over infinite case, which allows me to use L'Hopital rule. L'Hopital rule says take derivative of top and bottom and apply the same limit. So limit as b goes to negative infinity of negative 1 over negative 4 e to the negative 2b. Now, obviously, as b goes to negative infinity, this goes to positive infinity, the fraction goes to 0. So this part is going to be also 0, so you're going to just get 1/4. Okay, so you do need to use some of your 1a stuff for calculating the limits, but it is not much beyond what you're able to do. So it should be good. Okay, so this is how you handle with when one of your bounds are infinite. Now, when both of your bounds are infinite, then you have to actually split it into two pieces. So if I'm having an integral from negative infinity to positive infinity of a function, then my job is to split it into two parts from negative infinity to 0 or to some other point in the between, and from that point to infinity. So whenever you have from negative infinity to positive infinity, you are to split it into two pieces. calculate each of the two pieces and make sure both are convergent, then you're gonna add. And when I say convergent, I know that language may not be familiar, but convergent means you have a finite value for it. It gives you a number. It's not gonna go to infinity or not have a limit. So convergent means you have a limit. You're gonna come up with a number. Let me do the example. Actually, I'm gonna do another example from your homework. This is problem number 13 from 7-8. So it is integral from negative infinity to infinity of x e to the negative x squared dx. It's very similar to what we have done in the past, but we never had to deal with two infinite bounds here. Whereas here we have that, but let's see if we can handle this. So what I'm going to do is I'm going to look at two integrals. I'm going to look at the integral from negative infinity to say 0. And why did I pick 0? Because it was continuous over 0, and I like evaluating at 0. Things are going to usually work out nicely there. X e to the negative x squared dx, and then plus 0 to infinity x e to the negative x squared dx. So I'm going to consider both of those integrals. They both must exist and be finite for it to be a finite value. So I'm going to calculate, again, do the same thing. I'm going to calculate negative infinity to 0 of x e to the negative x squared first. And then I'm going to calculate integral from 0 to infinity of x e to the negative x squared. So I'm going to let limit as b goes to negative infinity of b to 0 x e to the negative x squared for this one. I'm going to take limit as b goes to infinity of 0 to b x e to the negative x squared dx. So I'm going to split it into two pieces, one that goes from negative infinity to 0, one that goes from 0 to infinity. Again, remember, the requirement is that both limits must exist, be finite for you to be able to do this. And then once you find the limits, then the sum of them would be what you need to have. So limit as b goes to negative infinity of, I'm going to do a u sub here. I'm going to let u be negative x squared, du is negative 2x dx. I have x dx, so I'm missing a negative 1/2 e to the u du. Now remember that I can also change my bounds, and I said just treat it like a definite integral. So if u is negative x squared, when x is b, it would be negative b squared. When x is 0, it's going to be 0. So it's going to be negative 1/2. I can pull that out. Limit as b goes to negative infinity of antiderivative e to the u is again, once again, e to the u from negative b squared to 0. Negative 1/2 limit as b goes to negative infinity, e to the 0 minus e to the negative b squared. Okay. Now, as b goes to negative infinity, b squared goes to positive infinity, negative b squared goes to negative infinity again. So it's going to be e to the 0, which is 1, minus e to a negative infinity. So this part actually from the limit goes to 0. So I get negative 1/2 as my result. So the negative part is negative 1/2. Does conversion gives you negative 1/2. So that one is good. Now let's see what the positive part is going to give me. Positive part, again, I'm going to do, as I did the limit, I'm going to do as u sub. I'm going to let u be negative x squared, same process. Du is equal to negative 2x dx, or negative 1/2 du is x dx, which is what I have. So the limit becomes limit as b goes to infinity of, now my bounds, 0 to negative b squared. Okay. And then I have e to the u du with a negative 1/2 up front. So I get negative 1/2 limit as b goes to infinity of e to the u from 0 to negative b squared, negative 1/2 limit as b goes to infinity of e to the negative b squared minus e to the 0. E to the b squared as b goes to infinity is going to go to 0. E to the 0 is 1. So negative 1 and negative 1/2 is 1/2. So the total is going to be 1/2 plus -1/2, which is 0. Okay. So that's all the cases of the infinite value. It's going to have either infinite on the top or infinite on the bottom, or I have infinite both. So those were the type 1 improperness. Next, we're going to talk about what would happen if you have type 2 improperness. That's the case where I told you guys we have discontinuity. Either we have discontinuity at the lower bound, we have discontinuity at the upper bound, maybe discontinuity at both. Sure. Or we have somewhere in between there's a discontinuity. And of course, that one is a very similar case then to this. We have to split it into 2 pieces. And then, yeah, we'll discuss it that way. But well, we'll get to that. So let's start with a very simple example. Suppose we have a discontinuity at one of the bounds, say lower bound. So the classic example of that one, of course, is for natural log. What is integral from 0 to 1 of natural log of x dx? Now, we are familiar with this. We have tools in calculating the antiderivative, but I'm going to pretend I don't know the antiderivative. So I'm going to just take the long way both. So you see how the steps work. And it's a good practice with the whole integration by parts part of this. So I'm going to write it as, so the way we do this one is, now remember natural log, the graph of natural log looks like this. So at 0, we have discontinuity, right? So at 1 is fine, but at 0, I have discontinuity, and I want to calculate this area, right? So what I'm going to do is I'm going to say, okay, I'm going to take integral from b to 1, just like before, but I'm going to let b go to 0 from the positive side. It is important to mention from which side, because as I said, depending on the problem, it may matter which side you're approaching your point. So I'm approaching 0 from positive side. Now, once you do this, once you get to this form, then now you just have a definite integral, no problem. And you can just do your, in this case, integration by parts. I'm going to let u be natural log of x, dv is dx, v is x, du is 1 over x dx. So it's going to be limit as b goes to 0 from positive side of uv, x ln of x, from b to 1, minus v du, x times 1 over x, which is 1 dx, once again from b to 1, all in the limit. So it's going to be limit as b goes to 0 from positive side of 1 ln of 1 minus b ln of b, we'll take care of that, minus x from b to 1, which is limit as b goes to 0 from positive side of ln of 1 is 0, so 1 times 0 is 0. B ln of b, we're going to have to take care of that, minus 1 minus 1 plus b. So now as b goes to 0, obviously this goes to 0, that's gone. We're left with something like this. So what is the question is, what is limit as b goes to 0 from positive side of b ln of b? Now, as you go to 0 from positive side, ln of b goes to negative infinity, b goes to 0, so 0 times infinity gives you what we call an indeterminate form. Again, back to 1a. So I'm going to rewrite it as limit as b goes to 0 from positive side of b ln of b over b. Something that goes to negative infinity, over 1 over b. Something that goes to negative infinity, ln as b goes to positive 0 from positive side goes to negative infinity, 1 over b as b goes to 0 goes to infinity. So both are going to go to infinities, which is an infinity over infinity case of L'Hopital rule. So you get limit as b goes to 0 from positive side of derivative of the top over derivative of the bottom. And that's just going to be limit as b goes to 0 of negative b, which is going to be 0. So this also is 0. So all I'm left with is -1. Process doesn't change. It's again, the trick is the limit. Bringing in a limit and trying to calculate that. Okay, now let's talk about one of the classic examples. This is one of the very conceptual examples in this topic, and that involves 1 over x, our friend 1 over x. Okay, so let me do it a version of it. Suppose somebody says, what is integral from, say, -1 to 1 on 1 over x dx? What would that be? Well, if you remember the graph of 1 over x, the graph of 1 over x looks something like this. And you're going from -1 to 1. So you're basically talking about this area. Now, to someone who just looks at this, they're like, oh, well, there is some area in here and some area here that will cancel out and going to be 0. Also, you could say, well, it's an odd function in a symmetric interval and the integral is going to be 0. But remember that property said that as long as a function is a continuous function, where this is not a continuous function, I have a problem at 0, 1 over 0 is not defined. So although it is convenient to say, well, maybe it's going to be 0 because the two parts are going to have the same area, one above x-axis and one below x-axis. But there's actually, there's a little bit of technicality that you cannot actually say that. And in fact, that turns out not to be true if you do this one, what we call the correct way of doing it. So the correct way is really writing it as -1 to 0 and 0 to 1, just like we did the example of double infinities. You split it into 2 regions. The idea here is both these integrals should exist and both of them with a finite value, and then the sum of them would be the value of the total integral here. Now, if you happen to be able to find each of those and both of them are the same value, one is positive, one is negative, then by all means the end value is going to be 0. But we have to first make sure they add up. They're finite. Each of them is going to be finite value. And it doesn't matter which one you start with. You can start with this one or that one, but it doesn't matter. So let's start with the second one because I think that's more natural for us. So I want to calculate integral 0 to 1 of 1 over x dx. So I'm focusing on this one. The idea here is if either one of those does not give you a finite number, then the total is not going to be a finite number. So you have to have a finite number for both to be able to add and get the total integral. So I'm going to rewrite this as limit as b goes to 0 from positive side. Again, you're calculating this one of b to 1, 1 over x dx. Antiderivative 1 over x, of course, is ln of x. So limit as b goes to 0 from positive side of ln of x. I don't need to put absolute value because I'm on the positive x values. So from b to 1, limit as b goes to 0 from positive side of ln of 1 minus ln of b. ln of 1 is 0. It's going to be limit as b goes to 0 from positive side of negative ln of b. And obviously, as b goes to 0 from positive side, ln of b goes to negative infinity. So that's just going to go diverge to infinity. So this area is actually infinite area. That's not a finite area, which means this one diverges, does not converge to a number because one of them did not converge. So it's very important for integrals like this, where you have a continuity in between, you have to split it to pieces that only have this continuity at one end and at the one endpoint. And then you can go ahead and calculate all of those should have an area and finite area, and then you can add them together. But this one is actually very interesting. This 1 over x happens to be a very interesting combination, but not from 0 to 1 version of it, but from 1 to infinity, which is what we're going to talk about next. But I hope you understand this. This is very important. If I had done a different one, say -1 to 1 of 1 over x squared, which seems similar, I'm going to again break it into -1 to 0 of 1 over x squared, and then 0 to 1 of 1 over x squared, which is going to be I have to calculate each one of them separately. So I'm going to do negative, and this time I'm going to do negative 1 to 0, 1 over x squared. Is limit as b goes to 0 from negative side, because you're approaching 0 from negative side now. Integral negative 1 to b of 1 over x squared dx, which is limit as b goes to 0 from negative side of antiderivative 1 over x squared is negative 1 over x from negative 1 to b, which is going to be limit as b goes to 0 from negative side of negative 1 over b plus 1 over negative 1 . Once again, as b goes to 0, you're going to have a problem. You're going to have infinite value there. So you end up again with something that's not convergent. Okay. Okay. Now, as I said, there is some importance to 1 over x, not from 0 to 1, but from 1 to x. In fact, let's do that. Let's calculate the integral from 1 to infinity of 1, just for fun, the dx. Okay, let's just do that. So what happens? Now, again, it's an improper of type 1. So this is going to be limit as b goes to infinity of 1 to b of 1 over x dx, which is going to be limit as b goes to infinity of ln of x. Again, since I'm on the positive side, I don't need to put absolute value, from 1 to b, which is going to be limit as b goes to infinity of ln of b minus ln of 1. This is 0. And as b goes to infinity, ln of b is going to go to infinity. So this is in divergence. Doesn't give you finite value. So the area under the curve of 1 over x from 1 to infinity, this is actually infinite. That's an infinite area. That's kind of like a settled argument. So okay, that's fine. It just happens not to be true. So it does not to converge. That's fine. That's just what it is. But let's do something here. Let's consider another one. Let's consider 1 to infinity of 1 over x squared. Just see what happens here. Again, we're just playing around, right? So once again, I'm going to let limit as b goes to infinity of 1 to b, which is limit as b goes to infinity of negative 1 over x from 1 to b, limit as b goes to infinity, negative 1 over b minus plus 1 over 1. As b goes to infinity, that goes to 0. I just end up with 1 over 1. I end up with 1. It converges. What a difference a simple power makes. 1 over x from 1 to infinity diverges. 1 over x squared, which is just slightly below this, that area actually converges. So the area below 1 over x diverges. The area below 1 over x squared actually is a finite value, converges. So that the simple, I guess the hand-waving explanation here is because 1 over x squared goes to 0 faster than 1 over x does. So you're adding smaller values, much smaller values faster than you do here. And then that's why it converges. But that's of course not mathematically precise. It's not rigorous enough. So we need to explain it more mathematically. So let's consider the case where we have integral from 1 to infinity of 1 over x to any p. Let's see what happens here. So this is the specific type of function we're talking about, whether it's 1 over x to the p, and p can be any number. Any number. I already established what happens if p is 1. So and you'll see what happens, why I do that. But let's suppose p is not 1, because I know when p is 1, that's the case of 1 over x, and that diverges. I already know that, so I'm not going to consider that as part of my group of examples. And because 1 over x in particular has a very specific antiderivative, that's ln. So that one I'm not going to worry too much about. So I'm going to look at the other possibilities. So once again, it's going to be limit as b goes to infinity of integral from 1 to b of 1 over x to the p dx. Let's write it the way we are more comfortable with. B goes to infinity of 1 to b of x to the negative p dx. Since p is not 1, I can just apply the power rule to this. I get limit as b goes to infinity of x to the negative p plus 1 over negative p plus 1 from 1 to b dx. Oh, sorry. Okay. So it's going to be limit as b goes to infinity of b to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Now, this part, of course, is convergent. As long as p is not 1, which is not, the denominator is going to be a non-zero number, and 1 to any power is 1. So this part is convergent, so no problem here. The question is what happens here? Does the limit of b to the 1 minus p over 1 minus p exist as b goes to infinity? As b goes to infinity, what you want to happen, you want the power of b to be negative, so it will be in the denominator, and as it goes into infinity, you get 0. So this converges if 1 minus p is a negative value, or if p is greater than 1. But if p is less than 1, then this will be positive power. You're taking something that goes to infinity to a positive power, it's going to go to infinity, so that diverges. And diverges if p is less than 1. In fact, also when p is equal to 1, it diverges, because we already know at the equal 1, it will be divergent. So the integral of 1 to infinity of 1 over x to the p dx is equal to 1 over p minus 1 if I push the negative through, when p is greater than 1, and diverges if p is less than or equal to 1. Now, I'd like to talk about this in this class, because next quarter in Math 1C, when you discuss sequence and series, there is a specific type of series that you will use for testing, and it's called p-series. And the process of showing convergence of p-series is very similar to that what I've shown here. So it's good for you guys to have seen it once here and then see it again next quarter in your 1C class. Okay. So of course, 2 is a number greater than 1. That's why it converged to 1 over 2 minus 1, which is 1. 1 obviously diverged. If it was like, say, integral of 1 to infinity of 1 over root x, because this is x to the 1/2 and 1/2 is less than 1, it diverges. So you get an idea. And if I say integral from 1 to infinity of 1 over x to the 3/2, because 3/2 is bigger than 1, then it's just going to be 1 over 3/2 minus 1, which is going to be 1 over 1/2, which is 2. So you get that. You don't have to necessarily memorize this formula, but it's convenient if you do. Okay. I hope this little presentation and doing examples that we did helps you understand this process a little bit better and then how to deal with the improper integrals. I will be making another video of doing some problems. If you guys ask me what type of questions you want me to do from these two sections, 7, 7, 7, 8, I'll be happy, more than glad to make another video before the due time. And again, remember, I moved the due date to Friday. So you guys should have more time to work on these. And then simultaneously, if you finish this, then please start working on chapter 8, 8.1, 8.2, which does feel a little bit lighter than chapter 7 after going through all this, but still it requires the time and focus to do well in it. But other than that, I hope this was a useful presentation. And if you have any questions or if you want me to do any particular problems, please let me know, and I'll be happy to do that for you. And thank you very much.